This week's topic is on electric fields. It splits pretty much into two sections. One is talking about the field strength and the related forces. So the field strength is related to one particle. The forces are the force acting between two particles. The second bit is all about electric potentials and potential energy. Again, it's a similar sort of analogy, but one is talking about vectors and forces, and electric field strengths are vectors, whereas potentials are scalars, and of course energy, as we know, is also scalar. But there are some analogies to be drawn between the two. There's also some analogies to be drawn between this and gravity. Okay, now, there's lots of bits and pieces really to go through. You'll notice that we don't need to study every single section, so do pay attention to which sections you need to study. You don't need to go on to capacitors, for example. Looks like there's a lot of information when you start to look at the section summaries, but in actual fact, this is just lots of bits of information. You don't really need to go into anything too conceptual with this. It's not as tricky as it looks. I am, in fact, going to skip ahead to electric fields and then to Coulomb's law. So the first thing to do with electric fields is it is analogous to gravitational fields. The strength of a gravitational field depends on two things: your distance to the object and the mass of the object. There's no difference in this case. The electric field strength depends on your distance to an object, but not the mass this time. It depends on the charge. And the first idea we come to doesn't have to be to do with point charges. It is just this equation, E equals F over Q. If you've got a charged particle and you've got a second charged particle, they'll experience a force of repulsion. If this has a charge Q and experiences a force F, then the electric field strength at that point there is F over Q. But the importance of this equation is a little bit more succinct than that. It basically tells us the definition of what an electric field strength is, and it is the force per unit charge. So for every coulomb of charge, this charge will experience a force of a value of the force of E. So if the field strength there was 10, then a charge with 1 coulomb will experience 10 newtons of force. Obviously, generally, objects tend to have charges which are a lot smaller than that. So, for example, don't forget, charging an electron is 1.6 times 10 to the minus 19 coulombs. So the forces involved at big distances are going to be a lot smaller. But when you do get into the electric field strength between objects like in an atomic nucleus sort of size, or even just an atom kind of distance, then the field strength can actually get very big and the forces can become a lot more tangible. Okay, so the main bits we're interested in really, more than anything else, are the force and electric field strength equations. You'll see them both there. There we go. So if you've got two particles, this equation uses Q1 and Q2. I'm just going to do it with big Q and little q. You can do whichever way you like, doesn't really matter. The force between the two particles, in this case it will be repulsive. Firstly, will be equal. They'll experience the same force because of Newton's third law. But as you might expect, the size of that force would depend on the two charges, or more to the point, the product of the two charges. But it would also depend on the distance of separation. And because this depends on the field strength, which is, or follows the inverse square law, so as you double your distance away, the field has been spread over an area which is 4 times larger. So the distance decreases proportional to r squared. And of course, there's a constant. You'll also come across this version of the equation, which is F equals QQ, or Q1, Q2, over 4 pi epsilon naught r squared. Doesn't matter which one you use particularly, but do make sure you use the right value for the constant for which one you choose to use. And please don't mix up this K with the Boltzmann constant. It is not the Boltzmann constant. Okay. Similarly, we've got the electric field strength. So in the first instance, this is the force between two particles. For the electric field strength, we've got one particle. And what I'm interested in is, at a point over here, at a given distance away from the particle, what is the value of the field strength? So this is a little bit like saying at a certain point away from Earth, what is the strength of gravity? This is exactly the same thing, except that it depends on the charge of the particle at the centre, rather than the mass of the planet in gravity. So the electric field strength equation is simply given by the constant. Again, it could be 4 pi epsilon naught on the bottom or k on the top. The charge of the particle and the distance you are away from it. So therefore, the closer you get, the stronger the electric field gets. It is an interesting little exercise just to try to figure out what the force between two protons in a nucleus would be. Generally, nucleons are approximately 1 femtometer apart, and 1 femtometer is times 10 to the minus 15 meters. Now, in reality, that's not quite true. We do have neutrons in the nucleus, and if you do the calculation for this, you'll see exactly why we have neutrons in the nucleus. So remember that each of these has a charge of E. Yes, I know E is the charge on an electron, but it is the quantized value of charge. Protons also have it. It's just positive. So both of the charges are 1.6 times 10 to the minus 19, and they are times 10 to the minus 15 meters apart. So use the force equation to work out what the force of repulsion between those two charges would be. Then you'll see why it is that nuclear physics contains a lot more energy, perhaps, than other forms of, other sciences, perhaps involving the electrons. You're going to get more energy out of the nucleus and doing processes in the nucleus than you would in, let's say, processes involving electron changes and chemical bonds and things like that. In other words, this is why an atomic bomb will explode with a lot more energy than any kind of chemical explosion. Just for one example. Moving on to, just again, make sure that you're aware you're not studying a couple of the sections at the end of this. It is just to do with electric fields and forces. So moving on to the potentials. So again, this is a little bit like potential energy in gravity. If you look back over your radial fields for gravity, you've got a different set of equations. You'll see there's an analogy here as well. So let's have a look. If I've got a particle of charge Q, and I take a second particle, that second particle has got a potential energy. So this is much the same as an object has a gravitational potential energy if it's placed above the surface of the Earth or any other mass. That potential depends on the size of the two charges and their distance of separation. The potential energy, you could call it EP, but more commonly you'll see it written as U. Can be a little bit confusing because we do use U as internal energy as well. There is a reason why they are related, but try and think of these as a bit of a separate idea. It's just an electric potential energy. We use the same equation idea as before. It's got the same constant in it, which is K, or it could be 4 pi epsilon naught. The potential energy, of course, should depend on both of the charges and their separation, but you'll notice this time it is not r squared. There is also the equivalent of the electric field strength in terms of potentials. So this is where you've got a charge, Q, and we're interested in the potential at a point in space, a certain distance away from that charge. This has a potential. Now, the same thing exists for gravitational potential, but it's an idea that people are much less familiar with. So it is a little bit like the first two equations that we looked at. It's the difference between having two particles and looking at the force of attraction or repulsion between them, whereas the electric field strength tells us what the field strength would be at a point, which basically says if we put a charge there, we can work out what the force would be. The potential is the same idea. The potential energy tells us the actual energy of a particular particle at a distance from another charged particle. Whereas what the potential does, not potential energy, but just the potential, it tells us the property of this point in space here, and would give us an idea, if we put a particle there, of what the energy it would have would be. So it's the potential, not the potential energy. Now, you have come across the idea of potential before, because the symbol for it is V, and you will have studied potential difference. Just literally to sidestep for a second, we don't really look at circuits as part of this course, but you've probably studied circuitry before on a basic level, and you'll have studied the idea of this being called voltage. But hopefully you'll have been corrected. By GCSE, you do start to refer to this as potential difference. If we just dismantle this for a second, and imagine it, instead of being electricity, but as being a water wheel, and the wires, instead of being electrical cables, being tubes that carry water. The water will power the water wheel. Now, granted, there's a little bit of a mechanics aspect to this one, so the analogy doesn't work perfectly, but it's just to give you a rough idea. There's a point there and a point there. What will drive the water down this pipe is the difference in heights, which is the difference in the potentials, or potential energies, of the individual bits. But you're looking at the overall effect, so it's just the difference in potential. That drives the circuit, but in reality it's the potential between here and here. So this side could be 3 volts, this side could be 4.5 volts. That would make a 1.5 volt battery. That's why it's referred to as potential difference, because it looks at the difference in the voltages or the potentials from either side. Okay. Doesn't really matter if you've kind of followed the idea of the circuits or not, but hopefully it gives you a bit of an idea of what we're talking about when we refer to potentials. What does matter is the equation. So the potential is just due to a certain point at a certain distance away from the particle. So it depends on the charge of that particle and the distance away from it. And again, it's not r squared. So again, we can just draw a little bit of analogy here between those 4 equations. So F equals K QQ over r squared. The potential, the electric field strength equals K Q over r squared. The potential energy U is KQQ over r, and the potential due to a charge at a point in space is KQ over r. So as you move from these equations to these equations, what you're doing, well, perhaps more if you move from the right to the left, it's easy to see what's going on. You're adding in this second charge. What we're really asking is, if I've got an electric field strength, or if I've got a potential, and I place a charge at that point, in the top equation, it will give me what the force of that is. In the bottom equation, it'll give me what the potential energy of that is. There is a way of looking at how we've got from the top to the bottom as well. It's probably easiest to see with the force equation, but we should remember the equation work done equals force times distance. In other words, this is an energy. Well, this is also an energy. It's a potential. So if we take this equation and we multiply it by a distance moved, then effectively instead of d we could say, oh, maybe that's r, also a distance. That cancels out, leaving us with the r rather than the r squared. That's not really a derivation as such, but it does give you the idea behind where these equations come from, and hopefully help you to understand the differences between them.